we are asked to set up 3 triple integrals, one in rectangular, one in cylindrical, and one in spherical coordinates that all find the volume that is bounded above by the cone z equals the square root of x squared plus y squared, and below by x squared plus y squared plus z minus 1 squared equals 1. Okay, so let's start by finding the bounds of the region in rectangular coordinates. So what we're going to need to do is start with a diagram. This is a sphere of radius 1 centered at 0, 0, 1. So I know everything I'm going to deal with is going to be above the xy plane. So there's the center of my sphere. I'm just going to try to draw as best I can. The hemisphere would be here, 1 unit away from that point. And there's my sphere. I broke one of my rules. I always draw the sphere first, but there's the sphere. Okay, but I'm bounded below by the sphere and above by a cone, so I don't even need the top part, right? Because if I think about the cone, z equals the square root of x squared plus y squared, that's going to come from the origin and actually hit that hemisphere all the way around. All right, so I'm below the cone and above that sphere. So it's like I took a bowl, a hemisphere that was solid, and I drilled a cone out of it. So it's a very small picture there, but that's what's going on. It looks like to me like you've made a bread bowl, right? You had this spherical loaf of bread and you carved a cone out of it, and so you've made a bread bowl. So what we're trying to do is find the volume of this bread bowl 3 different ways. Okay, well, if I project into the xy plane, my bread bowl would just be that hemisphere at x squared plus y squared equals 1, or the intersection there, that circle that is there. So there's my projection R. So I'm ready to find that rectangular coordinated integral. dz, dy, dx is the order in which I'm going to go. I would imagine that disk I just drew in the plane, I'd go perpendicular to it, I'd hit the sphere, and then the cone. All right, well the cone's already solved for z, so I can write that as my top bound. But the lower bound, now I need to solve that for z. So let's see. I would have z minus 1 squared equals 1 minus x squared minus y squared. I would then need to take a square root. Because I'm dealing with the bottom of the sphere, it would be the negative square root. And then I add 1 to both sides. So I get z equals 1 minus the square root of 1 minus x squared minus y squared. So there's my lower bound. That's not a really nice lower bound. I'm thinking maybe if I was going to evaluate this, I'd want to use either cylindrical or spherical coordinates, but I'm going to go on and finish the process here, now integrating with respect to y. I hit the bottom half of this circle and then the top half. And then finally, I need bounds for x that include the whole region, so from -1 to 1. And now I've found my rectangular coordinates integral. So let's now see if we can move into the cylindrical world. Well, thinking about this region in space, I know the cone, z equals the square root of x squared plus y squared, is z equals r. Already easier in cylindrical coordinates. And the sphere itself, I now need to think of in cylindrical coordinates, but I had it solved for z already. And so I realize that's 1 minus r squared under that radical now. So let's see. That triple integral would be dz r dr d theta. And still, this picture still works for finding the bounds. I go through the bottom of the bread bowl, the bottom part's the sphere. I exit through the cone. So those are my bounds. Those are a little bit nicer than the bounds I saw before. And now I'm dealing with this as a polar region. I start at the pole and I exit at r equals 1, so 0 to 1. And then I need to rotate all the way around. So from 0 to 2 pi. Comparing my rectangular coordinated triple integral and my cylindrical coordinates integral, I think this is the one I'd like so far. But now let's see if we can imagine this in spherical coordinates. Well, we've met we've met the cone, z equals x squared plus y squared before, and we know in spherical coordinates that's phi equals pi fourths. Now we need to think about this sphere in spherical coordinates. So that's x squared plus y squared plus z minus 1 squared equals 1. So let's square this. Right away, I can subtract 1 from both sides and make this be equal to 0, at least for a moment. X squared plus y squared plus z squared, well, that's rho squared. Minus 2 times z, right? The 1's gone. I just have that minus 2 times z. Well, I know z is rho cosine of phi. Rho squared is then 2 rho cosine phi. And dividing out that rho, I'm left with rho equals 2 cosine of phi. Okay, so now I need to think about this. I have the top and bottom as spherical equations. And now I just need to think about what the bounds would look like. Well, if I'm in that region, I'm below the cone or on the cone, and I always exit through the sphere, right? Because even if I'm going along the cone, I'm still hitting the sphere right there, and that's still in the region. So my bounds for a rho are going to be 0 and 2 cosine phi. So in spherical coordinates, my dv becomes rho squared sine phi, d rho, d phi, d theta. And we just established the bounds in the rho direction are 0 and 2 cosine of phi. Now I need bounds for phi. Well, going back to this time if I started on the z-axis, I'm not in the region. But when I lean over and I finally get into the region, I'm at pi fourths, right, where my cone starts. And then I have to rotate all the way until I get to the xy plane at pi halves to trace out the whole region. And so I found my bounds for phi, leaving theta. Well, I have to rotate all the way around to trace out the whole cone. So now we've seen 3 triple integrals, along with this one in cylindrical coordinates, that all find the same volume. I want you to pause the video here and pick one to actually evaluate. I don't know what you actually chose, but I would have chosen this one. In fact, I did choose this one, and I've evaluated it. And here's my solution. You actually get 1 pi thirds as the volume of this particular bread bowl. If you're taking this course as part of a curriculum at Alamance Community College, you can find this PDF on our Moodle page. If you're just watching this off YouTube, there it is.